All right, so far in our simple machines unit, we've talked about different types of simple machines that exist, and then within those different types that we could break certain ones down into certain classes. So if you think of levers, we have a first class lever, second and third class lever. Each operate in a different way, but the job of each is basically to do the same thing, is to make a process a little bit easier than it would be without that lever setup. Now, what we're looking into now is we're still considering the same machines that we've learned about, but what we want to do is we want to know how well of a job are they doing for us? How are they improving what we're doing in comparison to what we would do without these simple machines? And so a term for that is called mechanical advantage. So in doing work, we apply a force over a certain distance. When we use simple machines to help us complete tasks, we put in a certain amount of work, and ideally, in the absence of friction, we get the same amount of work out. We know that's not always true though. What changes is the amount of force and distance in the work input versus the output. And the system is the machine we're considering. For instance, it could be a first class lever. So really what we're doing when we're looking at mechanical advantage is basically just comparing how much work did we put in and how much work did we get out. Because if we use these, we can calculate a term called mechanical advantage, and we can figure out how well a machine is at doing its job. So there's two different types of mechanical advantage. We're going to start with the first one, actual mechanical advantage. So here's the key differences here. I'll try and highlight. So actual, here's the two we're going to talk about, actual and ideal. So actual mechanical advantage is the ratio of the force required to do the work without the machine over the force required to do the work while using the machine. So we call this the load force. So basically, if we didn't have a machine, what's the total weight of that load that we need to move or do something with? If we did have a machine, we call that the effort force, because now this machine's hopefully helping us out. So it's a scalar quantity, and the symbol AMA, or actual mechanical advantage, anything over 1 indicates that the machine reduces the required force. The bigger the AMA, the more the machine reduces the required force. And AMA can be calculated this way. So we take the load force, and divide it by the effort force. And that gives us a number below 1, close to 1, over 1, that tells us a little bit about how well this machine does its job. So what you're going to notice here is the second kind, and it's very similar except for this word. So we just looked at actual mechanical advantage, and here we're looking at something called ideal mechanical advantage. This is the mechanical advantage that a machine should have if it weren't, so let's say should have, if it weren't for friction reducing its effectiveness. We know there's friction everywhere in the world. It is a scalar quantity with the symbol IMA, so that's ideal mechanical advantage. And it's calculated, it's a calculated value and cannot be lower, cannot be less than the actual mechanical advantage. It's always more. So let's underline that as well. Cannot be lower than AMA. Each type of machine has a different way of calculating IMA, some of which are indicated below. So we'll go through those together, but here's our formula. So we have, in this case, the ideal mechanical advantage, we're looking at distances, comparing them, okay? And that's why there's different applications of this formula depending on the type of machine you're using. So let's just generally say this. The effort distance and the load distance. Okay, so let's look at how this might change a little bit depending on the type of machine that we're talking about. So levers we are familiar with, okay? When we're calculating the IMA for a lever, it's the ratio of effort arm length over the load arm length. So the effort arm is the distance between the point of applied force and the fulcrum. So applied force and the fulcrum equals your effort distance. And the load arm is the distance between the load force and the fulcrum. So load force and fulcrum. And we're talking about our load distance. And so it's always effort divided by load. Okay, because depending on the type of machine we're going to be looking at, that's going to change what it is that we're finding here. So for a lever, it's the effort arm length, or distance they use for this D, divided by the load arm length, and that tells us what our ideal mechanical advantage is for this lever. Now, what happens if we had a wheel and an axle? Okay, a wheel, if you picture, notice that the radius of a steering wheel in a car, where the effort is applied, so we apply our effort here on this wheel, it's much bigger than the radius of the axle. So the axle on a car, which is taking the load force, it means that there's a mechanical advantage. So the effort applied is much bigger than the radius of the axle itself. And so when it's a wheel and axle, we take the ratio of the radius of the wheel over the radius of the axle. So wheel over axle. And we're talking about radius here. If you remember, if we have a wheel, which is always going to be circular, and so these are still distances we're talking about. But in a wheel, because it's round, we're looking at a component or a measurement from that. Remember that radius is from the center, anywhere from the center of your circle to the edge. This represents our radius. And so the radius of the wheel divided by the radius of the axle tells us what the ideal mechanical advantage is if we're dealing with wheels. Okay, and we got two more to go through. So gears, if we're dealing with gears, they each have a certain number of teeth that lock into another gear with a certain number of teeth. And basically, if we want to calculate the IMA for a gear, it's the ratio of the tooth count in the effort gear. So let's just say this is the effort gear. This is the one that's controlling. You'll be told more when you're solving questions. You'll be told which one is which. And we're going to call this the load gear, what we're trying to move. So our effort's being put in using this wheel, and because these lock in, we're moving our load this way. So the ratio of the tooth count in the effort gear divided by the ratio of the tooth count in the load gear. So you would count how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. So our ideal mechanical advantage would be 12 divided by 8. Okay? These are pretty simple, straightforward examples. And our last example is when we're dealing with an inclined plane. Basically, our IMA is equal to our effort over our load. So our effort distance would be how far up this ramp do we have to get something. So effort distance. And our load distance is really, what do we want? We're trying to raise this box from the ground to this height. So our load distance would just be the change in vertical height. And that's DL. Okay, so what we've just looked at is calculating actual mechanical advantage and ideal mechanical advantage. And depending on which type of machine, simple machine that you're using, you're going to be looking at slightly different parts of that. So let's look at a quick summary of this now. Summary of machines and their respective ideal mechanical advantage ratios. So if we have a lever, we're taking the effort force distance to the fulcrum divided by the load. It's always effort first if you think about what's happening. If it's an inclined plane, the length of the inclined plane, because that's where we're applying our effort up that plane. So the effort first and load, we just need to change the height of that box. So that what becomes our load force. When we have pulleys, we have the number of supporting strings that exist. We didn't really look at pulleys in a lot of detail, so don't worry about that. If we come across an example, we'll use it. But wheel and axle, radius of the effort, so that's the wheel, and divided by radius of the load, which is the axle. And then if we have a set of gears that are grinding, the number of teeth on the load gear, the one that's controlling or moving, to try and get the effort one going. Okay. Actually, I'm just realizing this is backwards. On the initial page, these two are reversed. It should be effort divided by load. So these guys are reversed. Easy way to remember, all of your efforts are first, divided by all your loads are second. Okay? So we're going to look at a quick example. Determine the ideal mechanical advantage in each of the following situations. A piano is pushed up a 4-meter ramp on the floor of a van that is 1 meter from the ground. So we need to know our effort distance by going up this ramp, and our load distance, what's the total height. So here we go. It's a 4-meter long ramp, so 4 meters from here to here. That's our effort divided by our load, which is 1 meter, so we end up with 4 divided by 1, and we get an IMA of 4. A wheel with a radius of 10 centimeters is turning an axle with a radius of 2. Remember the wheel is first, that's our effort. This is our load. So we end up with 10 divided by 2, and we end up with an IMA of 5. And a gear with 18 teeth is driving a follower gear. So whatever one is in control, that is the one, that's the one that should come first. And in this case, they're calling it the load gear. Okay, I think they've just messed up backwards on this. That's okay. The driver gear, the first one, this is the only time it's going to be different. It's the load gear divided by the effort gear. Okay, yeah, so that's right. This is the effort, and the follower is the load. What they're trying to get to move. Okay, so in this case, it's reversed. It should be, so this is the 18 over here, 36 over here. So load divided by effort for IMA for a gear. Okay. And pulleys we didn't really talk about, but this is just a really simple example, and there's not much to it. You see a pulley here, so these are wheels, 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 and wheels, and they've oriented strings or chains or whatever it is they're going to use for this pulley around to create movement of some sort. And when we're looking at the ideal mechanical advantage, strictly speaking, it's just the number of supporting strings. So look at your pulley and see how many strings you have that are supporting. I've got 1, 2, 3, 4, and then 5. So 5 total supporting strings. That's my IMA. And that's it.